In this lesson, we will discuss how to calculate the minor losses in pipe systems. In a previous video, we examined the major losses in a pipe system, which are denoted by HL major and are caused by viscous effects in straight pipes. This video will discuss the minor losses, which are denoted as HL minor and are caused by viscous effects in pipe components. Before we begin, it should be noted that the subscript minor does not mean that the minor losses are always less than the major losses. There are many pipe systems in which HL minor is greater than HL major. In general, components affect the flow by changing the direction of flow, obstructing the flow, and changing flow speed through varying the cross-sectional area of the pipe system. Pipe systems may have many components. Bends, elbows, and tees are devices that change the flow direction. Valves are used to adjust flow rates. Expansions and contractions are used to slow down or speed up the flow and may occur suddenly or gradually. Entrances into pipe systems from reservoirs and exits from pipe systems into reservoirs are also considered to be components. Many components, such as the elbow, bend, sudden contraction, and sudden expansion shown here, cause the flow to change direction rapidly. This can lead to regions of separated flow, shown in blue, where eddies are formed. The presence of separated flow regions can greatly enhance losses in components. The geometry of many components are too complex to derive a theoretical expression for HL minor. Instead, the minor losses are calculated using an expression that is similar to the Darcy-Weisbach equation. For each component, the minor loss is equal to K times V average squared over 2G. K is a dimensionless loss coefficient that is obtained experimentally. Higher K values indicate higher losses for the same flow speed. There are many factors that can impact the loss coefficient: the size and geometry of the component, the Reynolds number, how the component is connected to a pipe, the proximity to other components, and the age of the component can all affect the loss coefficient. K values are usually reported in tables, equations, charts, or nomographs. For components that change cross-sectional area, the flow speed at the inlet and outlet will be different. For these components, the source that provides the K value should indicate whether you should use the inlet or outlet flow speed in calculating HL minor. Most pipe systems will have multiple components. When calculating the total minor losses for a pipe system, you need to add the contributions from all of the individual components. For example, let's suppose you want to calculate the minor losses for a pipe system that contains two 90-degree elbows and a valve. You would add the K value of elbow 1 times the average flow speed through elbow 1 squared divided by 2G, plus the K value of elbow 2 times the average flow speed through elbow 2 squared divided by 2G, plus the K value of the valve times the average flow speed through the valve squared divided by 2G. For many pipe systems, the pipe diameter does not change along the entire system. In these cases, the average velocity will be the same for all components, and the V squared over 2G term can be pulled out of the summation.